might ask, why do we have this like super accomplished scientist and researcher and actually computer scientist too? I just found out, I didn't know that before here. And I guess Neil and I met, I don't know if it was like 5 years ago, six,
Yeah,
I'm not
probably.
sure.
Yeah.
Yeah, I think when we first met, it was then. And I had started going, just even backing up a little bit, about 11 years ago, I started to go to science conferences and psychology conferences. And the main reason was I had read this book by Carl Jung, Synchronicity. And he was working with this physicist on, and the concept of synchronicity is a causal connecting principle. So it's when you have a coincidence that has meaning, but there's no causality. And I was actually having those in my life, and I kind of read this book, and it was like, okay, this is trying to give a scientific model, and part of that model involved quantum physics. And he was working with a physicist, Wolfgang Pauli, on the model. So and then of course Carl Jung, he came up with introvert, extroverts, the collective and conscious, the shadow, a lot of very important concepts in psychology. So I was also deep into that. But that led me into this kind of deep science hole, trying to understand the mechanics of things. And that's how I ended up meeting Neil. And we both have a mutual friend, a very, like, I guess you could say, world famous physicist, Manos Kafaros, who's he's dean of a physics department in California, in LA. And I've been, this is a very interesting subject, and it's definitely going to be something new for some of you. We're going to talk about the universe as a self-organizing system, and complexity theory, a lot of interesting things. I have been super interested in this relationship between order and chaos, and like in school, like I was, there was a lot of like structure sort of put on, but then I ended up competing in martial arts. And was it Tyson that said, everyone has a plan until you get punched in the face. But I competed in martial arts for quite some time, and you submit to chaos, and it's really, really interesting. But you can think of other sports teams like football. They have a plan that's got some structure, but then it's like that changes as they go. And so I've been interested in that. Another thing, I guess, speaking of chaos and self-organizing, I've been involved in creating one of the larger camps at Burning Man, and Burning Man has been a super interesting experiment. So Burning Man is a city that, about 80,000 people, and it's self-organized. They put a very basic framework on it, but it is all self-organized, and somehow this thing runs super well. So then they don't like post much for schedules, and you can't say when things are happening. So everything is emergent. So from a balance perspective, it's more on the chaos, but somehow some beautiful order, emerges out of that chaos. And also, like, even in the camp, we have a very large project, and it's actually like we use self-organizing. So and they're all volunteers. So it's interesting to see how we've been able to do, and our camp is actually the biggest build. So it's the most amount of work. So it's been interesting to see how we can use self-organizing to actually tackle this big, complicated project. And, finally, like, cities too have been fascinating. I was reading some research some time ago that shows how cities scale superlinearly. So, as cities get bigger, they get more productive. The GDP per person, salaries even get bigger. But on contrasting that, companies, as they get bigger, like in traditional hierarchical companies, it's actually sublinear. So the more people, the less productive you get. So it's like one of the theories is like, well, as we get better at self-organizing and more autonomous, can we actually become, like a city and become superlinear? So today, I guess we're, going to learn from nature, how nature self-organizes, and what can we learn from that? Is there something we can learn from that? And yeah, I'm super excited to introduce Neil. And we were just talking about this new discovery, the organ that was his work, which is super, I didn't even know that. So that's super cool.
The interstitium, ooh.
Yeah, so with that, I'd like to introduce and thank you, Dr. Neil Theise, for coming. Great to see you again, and I'll pass it over to you.
All right, thank you, Chris. Thank you, Erin, as well, for helping to get this going. Hi, everybody. So first off, out of what Chris just said, I would remind you that we and our organizations are part of nature. So when we talk about nature, it includes us and everything we do, even if what we do doesn't look like nature. I'd also encourage you, if you've got any questions, particularly if I'm not being clear about something, or if I use terminology where I jump off into some jargon and you want it explained, don't hesitate to interrupt. I guess Erin and Chris can monitor the chat window because I have a hard time keeping an eye on it when I'm also doing everything else, but don't hesitate to interrupt me. Or I'm hoping this talk will stay within bounds and give us a good amount of time for questions and discussion if you've got things you want to talk about afterwards. And regarding the interstitium stuff, the reason I told Chris to mention it is people do seem to be fascinated by that. It doesn't fit easily into the stream of this talk. However, if you wind up asking me questions about it, it definitely feeds back into all of this. And so we could explore that if you have an interest in doing so. And if you want to call it fascia instead of interstitium, I'm more than happy to do that for those fasciists out there. So the universe is a self-organizing system. Chris and I were joking this morning that the topic of the talk is everything. And that's true. But before, oh, how do we do this now? Oh, I have to click, okay. So this is you'll see this slide recur just to give you an idea of where we are in the course of the talk. I'll start off with what my points of view are that pour into what I'm going to show you, give you an introduction to complexity theory, and then really open up this idea of the universe as a self-organizing system. And out of that, with collaborative work I've done with Minos Kafatos, who Chris alluded to, and I'll tell you how we met, because that was a little bit of synchronicity, actually. No, it was a very big synchronicity. There's also some other synchronicity ideas, if you want to go back to that, really cool things I read recently, but okay. So how we characterize the functioning of the fact that the universe is a self-organizing system and some implications of that. Organizational structure and corporate structures are not my main bailiwick. I'll try to refer to that, but it's sort of implicit in everything I'm going to talk about, and I'm happy to focus more deeply on that in response to your concerns and questions and ideas. It would be interesting for me to explore that with you. So first off, my points of view, I'm a liver pathologist, which means I spend most of my day looking at stacks, let's see, no, this way, stacks of trays like that full of slides of patients' biopsies. This is a liver. Making diagnoses. So I look at human tissues all the time under the microscope. And that is important here, number one, because as a biologist, I'm a tissue biologist, which you don't hear about. You hear about cell and molecular biologists, but no one ever self-identifies as a tissue biologist. But that's what diagnostic pathologists are. We are studying the body at the tissue level. Not at the level that we see the cells, we see the molecules, we can stain them for them in various ways, but we're seeing how all of those come together as an ecosystem. And the other important thing about this is that I spend hours each day looking at tissues at the microscopic level. And so that means I'm constantly moving from the everyday scale like this down to the cellular level and then back again. And that's kind of a unique experience. The only thing that I can compare that to that I can think of for people is that pilots do the same thing. They're in the world and then they fly up every day and they're above the world. And you know that when you're flying in an airplane and you look out the window, to some extent when you're going up, but certainly when you're coming down, we've all had the experience of looking out the window and we see the world below us, below us, below us, below us. And then a couple of 100 feet above the ground, suddenly you transition into being in the world again at the regular scale. That moment of transition is something I experience all the time on my microscope. And that ability to scale up and down like that is the inability to do it is why this has been hard for people to see. It's why I have anything new to say about something. And I think this preconditioned me to see the kinds of things that I'm going to unwrap for you. And if you want to ask me about liver disease, we can talk about that too. There's always someone with a question about cirrhosis. And then 20 years ago, I got involved in stem cell research. It was my group that first confirmed that livers and human livers, not just mice, actually had stem cells. That was the turn of the millennium. And at the same time, within a month, we also showed that some of those liver cells were coming from the bone marrow. And those of you who are old enough, I see lots of young faces, so you probably think, yeah, every organ has stem cells and there are stem cells everywhere. That's not what we thought 20 years ago. And moreover, we thought that organs had stem cells that were restricted to those organs. And my group was one of a small cluster that in around 1999 to 2001 showed that the bone marrow actually had stem cells for every organ. Now, why this is surprising is that this is a fake diagram, but if you were to, it's like you could draw something you could draw for any organ or the entire body. Here you have a stem cell, an adult cell in an organ, or an embryonic stem cell in an embryo. And when it divides, it gives rise to a daughter cell, which has changed its gene programming to start moving towards a differentiated state. It's going to become something now, whereas the other cell replaces itself. So stem cells are always self-replacing. That's what makes them special. That cell then divides and gives rise to cells that change their genetic information again, expression, and some of those are self-preserving as well. And as you move down left to right in a hierarchical fashion along this tree, cells become what they are for the functionality of our body. So in case of the bone marrow stem cells become red cells and neutrophils and macrophages and eosinophils and neutrophils and plasma cells, all the different kinds of blood cells you have. And the dogma has always been for about 150 years that this is left to right. Cells do not go backwards and they do not jump. But the stem cell research from 1999 to 2001 started showing that in fact, all of these things could happen. My work in particular was showing this kind of thing, leaping from one lineage across to another lineage. And in fact, for those of you who are old enough to remember when George Bush gave his address to the nation about not needing to do embryonic stem cell research because adult stem cells could do everything embryonic stem cells could do, and therefore we didn't have to allow embryonic stem cell research, that was triggered by my paper from the May previously. His talk was in October. So unintended consequences. The anti-abortion lobby was thrilled with our paper. And when they started calling me to give talks, often to their church groups, I was a little bit surprised. But then I found the quick and easy answer was, do you really want this gay, Jewish, Buddhist, homosexual liver pathologist from New York coming to talk to your church group? And then the phone call stopped. So, done. But that's been a problem in stem cell research ever since. It got caught up in the politics, and very little has happened in that field. And I don't work in that field much anymore because of all that difficulty, which is a shame. But that led me to this complexity theory stuff. I was teamed up with an artist named Jane Prophet in the UK, a mutual friend of ours who had wanted us to meet for years, and we were never in the same city at the same time, thought if he got a research grant for the two of us, he would get us in the room together. And he got a Wellcome Trust grant for an artist and a scientist to meet 6 times, 3 in New York, 3 in London, to just share their ideas and record the conversations. They were interested in how an artist and a scientist would talk to each other and how creative new ideas could come out of that kind of interdisciplinary communication. And so we didn't have to have a product, a report or anything. We just had to have the conversations. And people actually have written papers on our conversations. I was speaking to her in the courtyard of the hospital, actually. I could show you the grass through my window. This was in 2001. where I was explaining to her about stem cells, some of the stuff there, and she said, oh, this is kind of like what they talk about in complexity theory about how ants self-organize. What you're describing about cells sounds like what ants do. And I had never heard of complexity theory, and she started to open that up. She's a really cool person to Google. Her name is Jane Prophet, Prophet. And what she was known for at that time was something called technosphere. It was a very early attempt to see how people interact with virtual creatures online. So this goes back to 1997, 98, I think she did it. And you would create these little creatures out of building blocks that she gave you, so everyone could build a different kind of creature, and you would send it off into the technosphere world, and it had programmed behaviors, and you could be an herbivore or a carnivore. I always, because of the Buddhist thing, I always picked an herbivore, and they never survived very long. It was kind of depressing. But then they would send you postcards about what was happening to them. Today, I outran a carnivore. I had a nice day just grazing. I got raped by an herbivore. I'm pregnant. I had a baby. All sorts of things could happen. But what they didn't expect was when people had sent in thousands of these creatures, the computer code, this was not visualizable back then. It was all computer code. The computer code started doing strange things, like normally there were births and deaths and the population would oscillate in subtle ways. All of a sudden it became completely stable. There were no changes. And when they went into, and then suddenly a population crash. Herbivores en masse died. It turned out that the herbivores had started to form herds, which had not been programmed, and they grazed their way into a closed valley in the landscape of technosphere. And the carnivores had lined up at the mouth of the valley. And when the herbivores ate all the food in the valley and decided to exit, the carnivores pounced. That was not programmed. That was what we're going to discuss as emergent self-organization in a virtual world. So this is how I got into complexity theory. And then while you might not think this applies, it really does. I have a lifelong Jewish practice, as well as a lot of academic study. Lately, some more mystical stuff. I'm a senior Zen student at the Village Zendo in New York, and recently fell into this shamanic stuff. And one of the things for both Manas and I, there are inextricable links between this stuff and our spiritual practices. And I'm not going to go into that in this talk, though it's certainly fair game. I will mention briefly a little perspective on that and how those all link together. But the fact is, if you take the science stuff and really follow it to its logical conclusions, you wind up with this stuff. And the fact that we were both prepared to see that when it happened, we weren't looking for it. But when it popped up, it was these practices. He's a Kashmiri Shaivist and now a little bit of a Buddhist and has a Greek Orthodox background. So we were ready to go. So complexity theory. Complex systems are self-organizing and adaptive. And so this is something when I'm talking to Chris, he's often talking about how all of you conceive self-organizing systems. But this is a subclass of self-organizing systems. These are self-organizing systems which are adaptive. Not all self-organizing systems are, and I'll give you some examples. So these are defined as groups of interacting individuals that if they fulfill 4 criteria, and these criteria I think are really useful when you're looking at any system that you're trying to assess or modulate in some fashion. These are good handles to bring to your analysis. They organize themselves from the bottom up into larger structures, which appear planned from the top downward, but are not. And these structures are referred to as emergent self-organization or emergence or emergent properties, and they are adaptive. That's a key thing. Sorry, I'm monitoring the election. Every time my phone rings, I'm hoping like Nevada called it. Never mind. Chris tried to talk about this earlier. We are not entertaining questions about this year's election during the question and answer period. Any other election, but not this one. So various examples where these ideas have been applied, this is standard modeling for economic systems now. This is how we understand them. This is how computer systems are developed to model them. It's employing these criteria. Chris mentioned urban development. If you know the work of the Canadian Jane Jacobs, The Life of Cities is her her initiating book of her way of seeing these things. She was writing about cities as complex systems before complex systems theory existed, really. She was intuiting that the structure of city arises from interactions of individuals at the ground level upward. And we might have illusions of top-down control, but in fact, that's just participation in the bottom-up phenomena. And we'll go a little bit more into city development down the line. It was my group, thanks to Jane, and some of our collaborators together, we formed a larger group who wrote about this fairly extensively, about stem cells and tissue development and repair of tissues. That's now part of the language. Beatlemania is my favorite. If you think the Beatles were the greatest rock band who ever lived, then Beatlemania is obvious. The Beatles created that. But in fact, if you watch the Beatles anthology, 10 hours of Beatle interviews from the BBC from a number of years ago, the Beatles over and over are very, very clear. It was the fans that drove their creativity. Everything they did creatively came about because of things to do with how their fans were reacting, including the fact that they could no longer hear themselves play. And so they withdrew into the studio to create Sgt. Pepper because it was impossible to play that music live and no one could force them to tour. And they talk about how that unpacked from those fan responses. So the Beatles' view of themselves is that they were responding to a created situation that was arising from the bottom up. Rise and fall of civilizations, evolution and speciation, all of these can be thought of in these terms. For you guys, corporate and structures and other sorts of organizations need to be discussed. And ant colonies, as Jane brought it up, it's a really good, useful, clear example, in part because there is no one who didn't hang out with ants when they were kids. Anywhere in the world I go, everyone played with ants or tortured ants when they were children. So this is kind of vivid. So here you have an ant line, typical sort of ant line, and you have the food at one end and the colony at the other end, and the ants are going back and forth, and there's your food line. And it's very clear it's a straight line. Now there are all sorts of structures other than food lines that ant colonies have. They have refuse dumps, they have cemeteries for dead ants, they have the whole apparatus of maintaining the queen ant, who is not monitoring she is not a top-down aspect of the colony. She simply serves a reproductive function. But that whole complex web of interactions around her is something that evolves from the interactions of ants. And an ant colony with 100 ants is complex. It has a lot of these structures. If you buy one of those little ant colonies that you can have on your desk with the green gel with 25 ants, that's enough to have a cemetery, a refuse dump, and tunnels. At 8 ants, and I know this because people have given me these things because they think I love ants, around 8 ants, you lose everything but the tunnels, and at 3 ants, it's just 3 ants wandering around and there's no organization, and then they die, and it's very sad. 100 ants gives you a certain degree of complexity, but with 1,000 ants, you get more complexity, and with 10,000 ants, you get more complexity. And so in terms of humans, a village is not a city, is not a megalopolis. So numbers matter. Not only do you need a certain baseline to have enough robust, don't get old, if you can avoid it. There's an English word for this, diversity. You have to have enough numbers to generate enough diversity to generate the creativity in the system. But also the more you have, the more complexity, the more that will arise in the system. This is a key thing. There have to be negative feedback loops in the system. So by negative feedback loop, I mean something like an air conditioner. The temperature goes up in the room, the air conditioner turns on, the room temperature comes down, the air conditioner turns off, and then the temperature starts to rise. And so you have this oscillation. So negative feedback loops always give rise to these oscillating patterns. Living systems are always oscillating. There's no such thing as stability. We'll come back to that later. Now, there can be positive feedback loops in the room. A positive feedback loop would be something like the hotter the room gets, the higher the heat turns on. So it gets hotter and hotter and hotter. Think about when you get a fever. That's a positive feedback loop taking over the system, driving your temperature up. So they can be useful, but they can't predominate. If they predominate, then you can still get self-organization, except instead of being adaptive, it's going to be energy expending and self-limiting. So think about hurricanes, tornadoes, cancer. And this way of conceptualizing cancer fits with the complex systems theory of how cells interact, because cells are inhibiting each other in all sorts of ways, by contact, by sending out signals. Our bodies are in this constant oscillating homeostatic mode. Cancer cells, by their genetic or epigenetic changes, start to delete those inhibitory negative feedback loops until you have an explosive cancer. And when I say energy wasting, I mean it. Why do cancer patients waste away? Because they're expending energy. And ultimately, it and the body it arose from will die. So they're self-limited. So when we say self-organization, that doesn't necessarily imply all this good stuff. The nature of the interactions that give rise to the self-organization condition whether it is in fact an adaptive living thing or a self-limited thing. Interactions are local without...
Neil, it's Scott here. I think I'm supposed to be the moderator, and there's a couple of questions that just kind of been lobbed up here. And I think you're touching on the first question right now quite well. But what distinguishes complex from non-complex? And then there's a follow-up question in there about when you refer to more or less complex systems, which measure of complexity are you using?
I'm not. That's not my headache. That's for mathematicians who want to quantify complexity. People go there, I don't go there. It's sufficient for my purposes to go that, a flatworm is not as complex as a sponge, is not as complex as a mouse, is not as complex. I'm not going to say as human, because a mouse and a human are kind of the same complexity. But that kind of thing. There's a body of work, and the mathematics is where I start to shy away. I will touch on it. The way I touch on it has been vetted by mathematicians. I've presented this in front of some very scary audiences, but I'll leave that for others. There's a lot of stuff out there.
I'm too really good with that, so let's do that.
Okay, that's fine. And the distinguishing complex from non-complex systems, it's that they fulfill these criteria.
Yeah.
So when you're dealing with, let's say you have a corporate structure, the extent to which it is functional, it may be a complex system, but it might not be terribly adaptive. And the sort of stuff Chris was talking about, it's because some aspect of these four criteria are not sufficiently robust or diverse. And eventually it becomes a dead thing. It ceases being a complex system, and that's a collapse. You can think of the collapse of the Soviet Union as being an example where there was too much top-down control. So there was no adaptive self-organization allowed from the bottom up. That's what made them vulnerable, for example. Or the flip side, too much freedom of interaction without negative feedback loops, that's economic bubbles. Welcome to America. So interactions are local without global sensing. No ant is monitoring whether there's enough food in the colony or whether there's where the next food is going to be put, or how do you find where to put the cemetery. It arises out of those things. Ants simply respond to pheromone signals between themselves and touching things, physical interactions and chemical interaction. Humans have a limited variety of ways of interacting with each other, although becoming more aware of subtle things in ways in which humans can interact, sort of energy stuff, for example, opens up new possibilities. How we shut that down closes possibilities. There may be people who think that they're organizing things, like the President of the United States, but the fact is they are simply a person interacting with a bunch of other local people that are feeding them information. That's also local interactions. There's no one who actually is monitoring the entire thing. we have things that simulate the global view, but that's why dictatorships fall, because there's always some little revolution over there they're not paying attention to, because they in fact don't have a global view. It's all local interactions. And then this is my favorite, there has to be some low-level randomness in the system. So if you have too much randomness, then the interactions don't self-organize into anything, you just have disorder. I wouldn't say chaos, we'll come to chaos in a bit. You have complete disorder. But on the other hand, if you don't have any randomness in the system, then there's no way for the system to explore new ways to interact, to adapt, and come up with new emergent behaviors. In which case, it's just a machine, like an air conditioner, doing exactly the same thing over and over again. And eventually that's going to break when the environment changes in such a way that the system can't adapt. Another phrase for this is quench disorder, which I particularly like that, but we might not have time to open it up a bit, but we'll put that in our pocket. So when you look at an ant food line, it looks like a straight line. But if you bend down and look more closely, there are always some random ants, divergent ants that aren't following the line. These were the ones that got into my mother's kitchen, and she would freak out when I was a kid. And being a proto-Buddhist then, when she wasn't looking, I would slip it on a piece of paper and take it out, because I knew if she saw it, she'd call the exterminator. She was right. The ants that aren't following the food lines are the likeliest ants that are going to find the new food source and start to establish the new food line. Those ants in her kitchen were getting ready to make a map for the ants to come get her food. The moment that if you step your foot in the middle of the food line, it's the ants not in the line that very rapidly find the most efficient route around your foot to reestablish the line. And it's around 2 to 4% of the ants. And that's a percentage range for all of these kind of randomness, however you measure it, that seems to be important. And this is what I was talking about with Jane, because I was saying how this unidirectional and hierarchical map of how stem cells give rise to tissues was dogma. And then when we had more sensitive techniques, we started seeing that in fact cells were moving in all sorts of other directions. But most of the experiments only showed this happening like 1 in 1,000 and 1 in 10,000 cells. So even when we proved it was happening, people who were opposed to the research said, well, it's happening, but it's a trivial amount. And Jane was the one who pointed out, no, it's not a trivial amount. This is the quench disorder, the limited randomness in the system that allows new tissue responses to develop in response to an injury or a change in environment. And that's what we subsequently wrote about. Now, this all has so those are the 4 main criteria. And I find it really useful whenever I'm thinking someone throws a system at me and says, is this complexity? Or how do we modulate this system, which is a complex system? Think about those 4 things. And if you come at me with the right questions, we can explore that a bit. But there are implications to this. And my favorite implication is the inevitability of mass extinction events. Child of Holocaust survivors, so I have a certain odd sense of humor. As Chris alluded, there is something called chaos, fractal chaos. This is a mathematical set of structures that are, another English word we're missing, it'll come to me in 8 minutes. Fractal, so that sort of not replicating. So at all levels of scale, no matter how high up you go or how down you go, the design of fractals looks exactly the same. Not self-referential.
Replicating.
Pardon?
Replicating?
Self-similar.
No, close.
Self-similar.
That's it, thank you.
Oh.
They're self-similar across all levels of scale. And then there's perfect disorder, like molecules in a gas. So this is not a real phase diagram, but you can sort of, again, this is past muster with the real people. There is order, disorder, and fractal chaos. Mathematically, complex systems lie at the boundary between fractal chaos and order. In fact, one of the best books on this, I think it's going to come up in another slide, from 20 years ago, but it's still, if you want a simple, full discussion for lay people, there are 2 books. One is by Roger Lewin, and he talks about complexity, life at the edge of chaos. And this is what he means. Living complex adaptive systems mathematically lie at this edge between chaos and order. Now, you might think that you could mathematically place any complex system at some location within that zone. However, because of the limited randomness in the system, the quench disorder, there is no fixed point for a system. It's always moving. So you wind up having this sort of path through the system. And given enough time, it will inevitably wander outside of that zone, either this side or this side in which it may freeze, or this side in which it may sort of explode. And when that happens, there's a mass extinction event, either of a piece of the system or the entire system. So the very thing that makes it adaptive, that quench disorder, is the very thing that guarantees with enough time the system will collapse. So the price of adaptation, of being alive, is the necessity of dying. There is no such thing as a fountain of youth. There's no such thing as eternal life, because what makes you alive also necessitates that you will die as a system. Any questions on all that? That's cheerful.
I've got a question.
Yep.
What happens if a system splits and one side is too orderly and one side is too chaotic?
I don't know if that happens. I suppose it could. I suppose that would be a mass extinction event. If they were completely chaotic or completely still, it would be a total mass extinction event. If either of them had enough remnants of the right zone of those four things, you'll have a new complex system. I mean, there are creatures which fission, right? Each of our cells divides all the time. So that sort of segregation into separate parts happens throughout. Sometimes it's the shedding of something. So a snake shedding its skin was originally part of the living system. But at some point, I don't know the mechanism of skin shedding, but at some point, some segment of the skin undergoes a mass extinction event and the living system proceeds, leaving it behind. So that would be an example of that, I suppose.
Thank you. That helps.
Neil, when
I
it
think
comes
I
to
spit out my water when he said that. Which one? Never mind.
that just got posted.
Some
I'm
things
curious
don't need to
about
be.
the controlled environment.
Oh, okay.
If you have a controlled environment,
Uh-huh.
and if you're self-organizing from the bottom up, a controlled environment would imply that there would be a top-down element to it.
Yeah.
How does that coexist?
Well, first off, a controlled environment, look at that as negative feedback loops.
Okay.
The rules of interaction can be arising from the nature of the beings, or it could be, a socialist system creates top-down control. Again, it's sort of an illusion, but it's a form of negative feedback. The question is but a completely controlled system allows for no disorder. Right? So it's fine. All of these things have to be in balance. And that's a sort of taste of how you can go into a system and analyze. You can look at a traditional mid-20th century communist system, and there was an attempt by an authoritarian government to control every aspect of communication in the population and economic production, et cetera, by setting strict boundaries, targets, and intervening harshly. And that works for a time, but it's also setting up other interactions that they're not in control of. And so revolutions happen.
Mm-hmm.
There are certainly aspects of people who study complex systems who look very specifically at top-down versus bottom-up. The terminology is confusing to me when it's simplified, but there was an example of a study I saw. This was in the New York Times like 10 years ago. I've been talking about this stuff for a long time, where they put people in a stadium and they looked at them from above so they could see the pattern of the people moving in the stadium. And they started them out in positions, and they each had an envelope which told them how they should interact when they were walking and bumped into someone. Should they go right or left or turn around? Should they stand still? And everyone got an envelope. But then they did that, and they saw emergent structures, emergent organization arising. They were shapes of the way people were moving with each other. Then they took a subset of people and gave them earpieces. And the people watching from above gave them instructions for how to change their behaviors. And so that was an intrusion of top down. And sure enough, you got different structures forming. The thing is it really top down? Because those people are just individuals who are interacting with their computer screens, watching things down below. It's also kind of just an extended version of local interaction. That kind of regulation obviously changes things, but is it truly top down? So the system can generate its own negative feedback loops, which then control the system. And that's also an emergent self-organization.
And then by essence, our feedback loops will continuously evolve.
Yeah.
It's not a static feedback loop, but rather they adapt according to circumstances.
Feedback loops themselves are emergent and adaptive structures.
Yeah.
Okay. Could self-organization potentially be a better word for us to use than self-management? That's for you guys to discuss later.
Yeah. We'll get to that, Megan. It's a good question. It's one that we've actually discussed a few times. So, but Neil, we'll let you continue, and then we'll cycle back to that after.
Andrew, yes, we'll get to that. Michael, yes, 3 slides from now, I think. So one of the things that we have you're anticipating me, don't do that. No, go ahead. One of the things that we see, we're way behind. Okay. I'll move it along quicker. You're too much fun to talk to. So another implication of cell lineages forming complex system is that we've already seen it, but we haven't really discussed it explicitly. Complex systems can exist in hierarchies. So an ant colony looks like a thing from afar. It may be changing its shape, but it looks like a dark spot on the ground. And when you go in closer, you see that it's not a thing at all. It's a phenomenon arising from interacting ants. But ants are bodies made of cells. So they're not things at all. When you go in more closely, you see that the ant body disappears as a thing, and it's just cells that are interacting with each other. So when you see things, so this means that whether something appears to be a thing, as opposed to a phenomenon arising from smaller things, depends on your scale of observation. So a bait ball of fish looks like a round ball from a distance. But if you see it and you're familiar with it, you know that these are fish. The fish themselves look like fish at this level of scale, but at the cellular level, there's no fish there. It's just a colony of cells. Murmurations of starlings looks like a thing, but it's not a thing, it's birds. Birds look like a thing, it's not a thing, it's cells. And our human bodies, only 10% approximately of our bodies are human cells. The rest is bacteria mostly, without which we would die. So the microbiome covers your entire skin and all the way through from your mouth to out the other end of your digestive tract, up your nose, into your sinuses, your lungs. There's bacteria all through there, without which you can't live. You're not a living human being without the 90% of your cells that are actually not your cells, bacteria. For example, a crease at the edge on your skin, that always has a range, which bacteria there are different from person to person, but what they all have in common is that these are bacteria that feed on the cell membranes of dying skin cells. And when they feed on that, what they excrete is lanolin. And so those bacteria create lubrication, and that's why your joint skin doesn't crack. And that's why they do crack if you use too much sanitizer and you kill all the bacteria. So your body is not a living system if it doesn't have trillions of bacteria. They are as much a part of you as your human cells, even though they don't share any of your DNA. So at the cellular level, you are a community of cells. You're not at this level of scale, you're those objects on my screen listening to this object talking. At the cellular level, not so much. And this idea that it's scale dependent, that you are a thing or a phenomenon arising from smaller things, and both are true, that this depends on the scale of observation, the method of viewing. This is when I started working with Manas, and it was this point actually we came together. This is a form of complementarity. The word was chosen by Niels Bohr, the father of quantum physics, talking about wave-particle duality. Quantum phenomena exist complementary aspects that are revealed by specific observations, i.e. there are a range of possible states prior to observation, and any single observation is unable to capture all aspects of the complete physical situation simultaneously. He not only called this wave-particle duality complementarity, but he extrapolated that the entire universe, everything in the universe, was nested complementary systems. It was not simply a quantum physics concept to him. And this is one of the things Manas and I have written about together. I don't have time to go into the double slit experiment, but this is that thing that if you look at light in one way, it looks like it's behaving like a wave. If you look at its particles, if you look at it the other way, it looks like it's behaving like a wave. And you can never see both at the same time. It's like this. Is this two faces or a vase? Of course, it's both. But you can only actually see one version of it at a time. People have done fMRI things. You can move very quickly between them, but it's really hard to actually see both simultaneously. If you say it's two faces, you're correct, but it's incomplete. If you say it's a vase, you're correct, but it's incomplete. You need both views to get the complete view. Are each of us living things? Yes. Are each of us colonies of human and bacterial cells? Yes. And you have to select how you're going to view it and interact it. So I look under the microscope and then I come back up and see the person sitting opposite the microscope. Another way to diagram this is cells self-organize into bodies and bodies into communities. And depending on how you define a body, this could be organizations, cities, ecosystems, Gaia. So James Lovelock, like Jane Jacobs, long before complexity theory had really arisen, he was intuiting that the entire Earth was a living system and thinking about it in terms of complex systems theory, which had not been formalized into jargon at that time. So does this mean cells are an actual thing? Well, when we talk about cells, we're talking about Western medicine and Western biology. When we use those terms, we mean how biology is viewed through cell doctrine. Before the microscope is invented, no one knew if the body was an endlessly divisible fluid continuum, or was it made of indivisible subunits that they called atoms. And when they looked under the microscope and they saw cell walls and cell membranes, you had a box with 4 walls, a ceiling, and a floor. That you can't subdivide a box. You don't get smaller boxes, you get pieces of the sides of the box. So indivisible subunits, those were atoms, and they called them cells because it looked like the empty room of a monk or a prisoner, a monk's cell or a prisoner's cell. And then later, when they started to apply stains, like I look at under the microscope, they saw the other bits of stuff inside the cell. So they saw the furniture, but they didn't go back and say, oh, we were wrong. Cell doctrine was born. And when we say Western medicine and Western biology, that's what we mean. Bodies are made of cells and all cells come from other cells. So are cells a thing? No. Biomolecules are floating in water and they self-organize into the larger cell. At the cellular level that I look at under the microscope, cells are things. At the nanoscopic level, they're simply molecules floating in other molecules, the other molecules being water molecules. And they interact with each other through all those same criteria. This is where the quench disorder literally becomes quench disorder. I have to speed through this, but if you want to return to that, it's kind of cool. So are molecules a thing? Of course not. Oh, wait, let's insert an important concept. This now introduces the issue of boundaries. So at this level of scale, our boundary is our skin, and that's true. But at the cellular level, we're shedding bacteria and dead skin cells all the time. The dust in the corner of your room is mostly shed skin cells. And if you live with anybody or pets, in fact, if you go look at your microbiomes from the people living in an apartment together, or spending too much time in corporate cubicles together, they share their microbiomes. Every time you shake hands, every time you kiss someone, every time you hug someone, anytime your skin comes in contact with a doorknob or anything else, it transfers it. So you touch that doorknob and some of your microbiome goes on that doorknob. Someone else comes through that door, they've picked up some of your microbiome. At the cellular level, where are your boundaries? At least as big as the place you live and work. At the molecular level, well, we're breathing out oxygen all the time. No, we're breathing out carbon dioxide for all the plants. And they're breathing out oxygen from the carbon dioxide they got from you. And it's this cycle. At the molecular level, where is your boundary? Your boundary is the entire living biomass of the planet, because molecules are being exchanged across that biomass all the time. So boundaries are also not things. They are dependent on your scale of observation. And so this introduces the question of hierarchy. We're really not talking about hierarchy. We're talking what Arthur Koestler called holarchies, because each of these things is always there. You can only see one aspect at a time, but they're all in complementarity. In quantum physics, if you know superposition in quantum physics, this is the biologic or large-scale quantum version of superposition. So holarchy is actually better. These systems are not one on top of the other. It is not, in fact, top-down. And that's one of the answers to that question, is anything top-down? No, it's a web. But you're always selecting a view. So biomolecules, they're nothing but self-organizing atoms. So where is your boundary if you're made of atoms? Well, there is, in fact, no atom in your body that you do not breathe, eat, or drink from the planet. So at the atomic level, we're walking, talking Earth. We are simply how the atoms of the Earth have interacted with each other to eventually self-organize into people. And when we sent Curiosity to Mars, you can look at that quite correctly, that there are some brilliant scientists and engineers at NASA who figured out how to send a robot to Mars and then send signals back. But it is also complementarity, just as equally true, that it took 3.5 billion years for the atoms of Earth to self-organize in such a fashion that Earth could reach out and touch Mars. That's not fantasy, that's reality. It all depends on your perspective. And atoms are just nothing but subatomic particles, which are nothing but smaller subatomic particles. And then you get down to where physicists don't agree. This is where string theory comes in. One thought is these are little mini vibrating strings, but there are other theories out there. There's no agreement. But it's not endlessly, infinitely smaller and smaller. This level is the smallest you can get. And that's an implication of quantum theory. We talk about Planck length and Planck time. There is a tiniest. And this is where we find the tiniest. So are these the ultimate thing? Well, these have no inherent existence either, because these just pop in and out of the vacuum. The vacuum is not, in fact, empty, like we typically think of a vacuum. It's energy rich, unavoidably. It's an implication of quantum theory. And because it's energy, Einstein equals mc squared, it pops up into these little tiny things, which usually matter, antimatter, bump into each other and self-annihilate. But there are exceptions to that. And when those exceptions happen, these things survive. And because they can interact with each other, they self-organize into subatomic particles, into atoms, into molecules, into the entire universe. This is called the quantum foam, this movement in and out. And mathematically, as well as theoretically, the quantum foam and the quantum vacuum are the lowest level complementarity, one might say. And from that, in those interactions, it gives rise everything, including the large scale structure of the universe. So this is the universe as a self-organizing system. So we don't live in the universe, we are the universe. This is really sort of, I think we can skip the 3 laws. But
Neil, we're at
time.
at the top of the hour.
Yeah.
So want to encourage you to continue, but I know for some of you, there might be, this was scheduled for 1 hour. So if it's okay, Neil, to continue to run, if you're okay with that.
Yeah,
Let's do that.
Yeah.
The next session is not until for another 35 minutes, but for those of you fully understand you got meetings or some commitments, don't hesitate to go do those. But if you're free to stick around I encourage you to please do so. So I'll turn it back to you, Neil.
Thank you. Yeah, I'm sorry. I was having too much fun talking to you and I wasn't paying attention.
No,
but
no,
we
no,
are
it's
sort of
fine.
at the end. So is this everything? And theoretically, from a purely Western science point of view, this is everything. This is the theory of everything. It is one way to show how we go from the quantum scale to the universal scale. But we didn't stop there because Manas and I both have these backgrounds in metaphysical studies, shall we say. And so this paper, you can look up online. I'm not going to go into it in detail, but basically we look at how Western philosophy is in accord with everything being that mind doesn't arise from things. Things arise from one substance, as Spinoza said, or mind. So we review that in this paper, the science we've touched on, and all these different metaphysical systems. And if you give weight to these as being real experiences, then the inevitable implication from all of these three things, Western philosophy, Western science, and all of these cross-cultural practices, is that underlying this is pure consciousness, pure awareness that's non-dual, no subject-object. And the universe arises when subject-object split starts to occur within that pure awareness. And that's a whole other hour. So I'll leave you with this. Here's each of our bounded little bodies. Boundaries are where one gives and receives. This is where things come and go from inside to outside, right? But we know that this boundary view is dependent on scale, and the lower, dependent on scale of observation. The lower down in the scale of observation you go, the wider your boundary goes, until you finally wind up in the quantum realm. And that's where bodies have no boundary. The boundary is the entire universe at the quantum level. That's non-locality. In the realm of this boundless body, there is nothing to give and nothing to receive. Or as one of my Zen teachers said, no cell, no self. Thank you.
That was awesome, Neil. I think heads exploded at the "We Are the Universe" portion.
True. But can you feel it? That's the question.
I wonder if I've got some feedback loop. I want to open up for questions. If it's okay with you, Neil, if we can.
Please, yeah. I'm at your
So I
service.
just encourage, if you have a question, maybe just unmute and lob out the question. I'll stay quiet for a moment to let people do that.
I'm interested by your mention of boundaries right at the end there. And I'm wondering, it's been a topic that's been on my mind for a little while now. It seems essential for organization to have boundaries. Is that kind of what you're getting at there?
Well, boundaries are inevitable, but how you define them, there's always boundaries. But where those boundaries are is not fixed. It depends on how you're observing the system. So you come in, you're existing within a system and you feel yourself being this cog in the wheel. That's probably a dysphoric state. It's probably not a well-organized, it's not an adaptive system, kind of how I feel like in my hospital cubicle often. Hospitals are not always pleasant places to work. Or you can be part of a group, let's say jazz musicians playing, and there's no boundary there. Their experience is loss of boundaries. When you're in the flow, as people say, in any sort of group dynamic, part of what's the change in perception in that flow state is you don't stop at your skin. Good sex versus bad sex. Two people in a room doing things versus what?
That's interesting. I wonder though about the relation of things like Dunbar numbers and like you've got the 5 jazz musicians and they're just in a flow state and they're jamming out, right? But you pile in a bunch more people and you lose the jazz, or you need to differentiate, it seems, the musicians from the rest of them.
Well, that's interesting. I I suppose if you suddenly increase the numbers of the system, because the 5-member group is not in fact bounded from everything else. You may put them on a stage and say, here's the boundary, but introduce an audience into a room or take that audience away. I can't stand doing these online things where I'm not allowed to see faces or at least photographs of faces looking at me. It's a completely different experience. And if you bring in new numbers, well, there's going to be time where the modes of interaction that worked at 100 ants, other things are going to start happening. There's going to be changing and there's going to be shifts in the system. But then you will come to new equilibria, hopefully. Depends on what you introduce. Yesterday I was in the New York City Protect the Vote March, where the cops were on the outside and everyone was marching down Fifth Avenue and everything was fine. At some point, those boundaries disintegrated and I left the march early, but then it exploded in disordered violence, which was, we were existing as a flowing group that was adaptive. It was amazing to watch how people walked in the group and how there were sort of waves that traveled up and down the avenue, and that chants would come and then they would go and then another chant would arise. At some point when it got into the village, I wasn't there to see what broke down, but something was changing in the interactions. It might simply have been the narrower streets, so the cops being more restrictive, so more positive feedback loops and not enough diversity of interaction to give robust negative feedback loops. And so you had a mass extinction event.
So was the boundary an illusion in the first place? What was that boundary? Because we had the system, right? And we can say there is inside the system, there's outside, there's the marchers, there's the police. But at some point, like those police were always there. The marchers were always, I wouldn't say always marching, right? But we could identify them. But then at some point, did the system change? Did more get added? But they were there.
Well, like I said, I think the Fifth Avenue is really wide. So you had a sea of people inhibiting the police from going in and doing anything direct. And then you get to the Greenwich Village and the street suddenly will allow 5 people to go side by side instead of 30 people to go side by side. And so now the ratio of police to people has increased. You're also in a residential area, and apparently some of the residents were yelling at the marchers. More top-down, you know. So, but what you said about boundaries being an illusion, they're never an illusion, but they're always contingent. There are always boundaries. The question is, where do you see the boundary? Where you locate the boundary depends on how you view the system. The only time there's no boundary is when you're talking about being a Buddhist meditator and experiencing the absolute, or a Christian mystic and, you know, cleaving to God, or you're a quantum physicist and you're experiencing the universe as a quantum system. That's the only time the boundaries disappear. But it's still the boundaries of the universe, but you're in it.
Thanks.
Great stream of questions there, Andrew. Pwach, I see you with you're not muted, which usually tells me you've got a question, but maybe I'm just making an assumption. If there's any other questions, or
it's a decent assumption. I do actually have a question about the. So obviously, there's complex adaptive systems. We know evolution due to adaptive nature of all the agents in the system. I'm just curious about the jumps in evolution, and like if in the complex organization, we have these events that causes certain sorts of revolution. And I think there's even a debate in the evolutionary scientists whether that is a case or that is a bullcrap. But it's obviously we can even experience it these days as our world gets more complex. We have these either black swan events in economy, in the society, and like there's all these things. So I'm just curious, like if you go back down to the sort of the theory of it, like what would be conditions in the system, and possibly how can we nurture conditions in the system to actually get that jumps in whatever we would like to see jumps.
Right. So it goes back to those 4 criteria. So I was part of a conference on peacemaking in Ottawa, and there was a woman there. I just published a paper with her, so if you Google me, you'll find her, but I'm blocking again. Catherine Twinn, there, Twinn. She's so she was discussing, she comes from the Native community of Canada, and she was talking about conditions on their versions of reservations and depression and alcoholism and interfamily violence and et cetera, et cetera, et cetera. And how to get around that. And what we do as Westerners is we go in and we prescribe medications for the depression. We have 12-step programs for the alcohol. We arrest people who are violent and put them in prison. And that's not really helping. What they've lost in being moved to reservations and deprived of their culture are things that were already there in the system, such as storytelling circles. So we started to analyze what were their original customs that helped facilitate negative feedback loops. Jane Jacobs talked about the failure of New York City public housing. The original idea was you'd have these tall towers surrounded by green areas. And wouldn't that make for a really good organization for a city that would be peaceful? And instead, what you got is still today, the violence of the projects, completely disordered. What she identified was that in Brooklyn, where you had the same socioeconomic status, but people lived in row houses, you had grandmas sitting on the stoop or leaning out their windows. You had eyes on the street. And that is a social interaction that creates a negative feedback loop. When there's no one in the hallways and there's no one in these vast green spaces, then anything can happen. There's no inhibition. So you can go into the system and say, are there enough people here? Are there enough interactions here? What are the nature of the interactions? If a company consists of 100 people sitting in cubicles with performing functions that are being given by a manager up top and they never talk to each other, there's not a lot of creativity in that system. There's not a lot of diversity. But if you put into that system occasional gatherings at lunchtime, that serves a purpose for exchange of information. The more diverse, you get more diversity with more people, you get more. This is why the Wellcome Trust was so interested in interdisciplinary communication between Jane and I. If you have scientists talking to scientists, everything happens the same way. The problem solving is always the same. Artists with artists. There's sort of set patterns that have evolved for how they interact. But you put an artist and a scientist together, new things happen. So to me, and what I imagine you folks are trying to do is you go into a system and you look for diversity of interactions, diversity of communication, diversity of participants. Are there too many control points? Are there enough negative feedback loops that are homeostatic to give a living system? Are people aware of themselves as they're interacting and realizing that even if they're in their separate cubicles, but they're talking to each other, those interactions themselves are in fact local, even if they're completely physically separated? An organization that consists of people in cubicles around the planet, they're still local if they're talking to each other. And then is there any chance for randomness in the system? Just tell everyone to do what they want to do, you're not going to get anything productive. But if everyone is doing exactly the same thing. So these are the ways I explore, whether it's social systems or scientific systems. I look at those 4 criteria and I think, where is there something off balance here? Or what if you made a shift in this direction or that? And then inevitably it's going to change over time. So this isn't something you then set and then never have to look at it again. Is that the kind of thing you were asking?
Yeah, that's okay.
Okay.
Awesome. Just with Neil, this is phenomenal. CK, do you want to take a moment to cycle back to Megan's question about the self-managing, self-organizing within the context of Neil's presentation?
And when we call you CK, is that what we call you?
Yeah, that's
Okay.
Among other things.
We've had lots of discussion, about like what do we call this? So one of the problems with self-management is that it just refers to like the individual managing himself. It doesn't actually cover the hierarchy as Neil said. And as you know, with our system at the very base level is principles. And then we have practices and process, and the top is architecture. The architecture that we model from is based on a hierarchy where this is founded on the concept too of complementarity, where everything is both a part and a whole. The part thinking of the particle, the whole being the wave. And so it offers those two views of looking at it. And if you look at Thiel, there's a concept too of complementarity. One of the when you get to the higher levels of human development, and in Thiel, it's second tier thinking, it's described as being able to hold contradicting points of view at the same time. And this is exactly what complementarity says. One of the things that Niels Bohr said is, you're at a deep truth is when you have found opposites that together make up the same thing, because that's exactly what complementarity was, as this universal principle. So we can start to take a look at that model and from a mental perspective sort of see that, and what we're seeing right now in the world that is kind of triggering polarization is one side or the other perspectives, and not having a complementarity view, and the feedback loops are actually reinforcing one perspective or another perspective, whatever echo chamber you're in. So we're also seeing a rise right now of actually more non-second tier type of thinking because of the media field. But our system is actually ordered. When we looked at the system, it's like, let's take second tier thinkers, let's take Thiel or self-transforming, and the process just to be inclusive of other levels. But that's the approach we took. But yeah, it's a good question. Self-management is what it's sort of being described at from like an industry perspective as a category, but it may not be the right term, and we maybe need to consider something that's more holistic.
Yeah, very good point. Neil, you look like you were going to say something there.
Yeah, a bunch of things. Everything triggered something. So I hadn't really thought about this, but everyone keeps pointing at Facebook and Twitter as driving this, and I haven't thought about it in a complexity perspective. But what do their algorithms do? They're positive feedback loops.
Yeah.
They're designed to be positive feedback loops, which drive more and more of itself. And the more you have, the more you get. And so our communication systems it looked like it was going to be greater diversity of an oscillating adaptive system, but they put into it these positive feedback loops, which have led to energy expending, self-limited, system's going to collapse, rigid, non-adaptive structures. So it gives a perfect way to understand what Facebook and Twitter, et cetera, did.
I would just add that exponential tech, if you want to follow complexity theory, basically accelerates self-terminating.
Yeah. Now, another point that you touched on is one of the things that how I enter into an analysis often, I keep these four things in mind, but another way I enter into analysis is okay, I'm entering into the system I'm thinking about at this level of scale. What if I make myself consciously think about it at what comprises the level of scale below that? Mm-hmm. What comprises the higher level of scale above that? And see how that shifts, how the boundaries change. Yes, I'm inside my hospital as an individual, and that's mostly my view, and it's often unpleasant. But during the COVID thing, I'm in New York City, it was NYU. We became a COVID hospital with 1,000 patients on 18 floors. The coherence of the system that arose to that occasion was extraordinary. And everybody here felt that. I've never been proud of my institutions before, but suddenly it was like we were all somehow it synced. Part of that was top down, but our top down management, this institution had already been destroyed by Hurricane Sandy. They understood what it took to recover, and part of that was distributed management, distributed organization. So ideas were popping up for how to handle this in different floors, and that within 5 days they were integrated into the system response. So thinking, entering in, and making sure you're looking at different levels of scale. In terms of terminology, one of the things I didn't go into, I mean, it's hard to, you've got structures that like to talk about management. I mean, at Wharton, they're going to talk about management. That word's going to get in there. One of the things that, am I still on share screen? Yeah.
You are, yes.
So early terminology that Manas and I were using for how things are interacting, and that gives rise to everything, was we met because I called all of it sentience, and I said the entire universe is sentient, and I gave a talk that he heard about this, and he said, I think you're the person I'm supposed to be talking to. You need to explain to me what you said. And we started talking, and everything came from that. People really were like, you're not going to tell me atoms are sentient. It was like, okay, we won't. Let's keep sentience for biological systems. But molecules and atoms are creatively interacting with each other, and they are bounded systems. But at the quantum level, there are no boundaries. We're talking about intraactivity because of non-locality. And I wonder whether this terminology, while it technically speaking, it's really only at the quantum level, from a metaphorical system, to talk about creativity arising as an intra-activity rather than interactions, they're intra-actions, which is the same as saying holarchy versus hierarchy. Are these terms useful to you? I don't know, but they popped into my head.
The language is appealing. The language is definitely appealing to me.
But then we went to process following Whitehead, which is a thing. And now Manas wants to call it flow.
That was my suggestion, by the way.
Yeah, which? Flow?
Flow, yeah. I was just playing. I mean, there's some parallels to it. That was a term coined by Mihai Csikszentmihalyi that, he's one of the fathers of positive psychology. He's at Penn State. And he, that is there are some parallels to what is being utilized there, but I thought that the term, it was becoming popular like many, many years ago. And in fact, a colleague of ours wrote a book, the synchronicity of flow. I was actually going to have him here, Sky Nelson. I think you know Sky, you met him?
No.
Okay, he's a physicist too. I had met him many, many years ago, and he ended up, and we were discussing this, but yeah, that was a suggestion that I had, but I'm still.
Thanks for that.
Yeah. I think we need, there needs to be terms that really can connect to the masses. And so I'm not sold on what, the sign, like complementarity is definitely the right term, right? Recursion is probably the right term, but yeah, it's.
But these are scientific papers we're writing. So my primary purpose is clarity in a scientific way. Yeah. And when Manas goes off on a toot, and I'm like, all right. Yeah. He's very senior to me, so I just have to go, okay.
Yeah, I'm gonna jump in here, guys. You two are gonna keep going forever. So if you want to chat it, you guys do that. Yeah. But we've only got 10 minutes before the next session, and so I want to let people get at least 10 minutes before the little bit of a break. Neil, thank you so much. This is absolutely fascinating. And I love the fact that it's bringing in different perspectives and disciplines into our Leads Week. And it is very helpful for us to understand ideas and perspectives from those different disciplines and forcing us to think a little bit differently about how we're looking at things. So thank you so much for doing that. That was an excellent presentation.
Quick last thing, I'll send to Aaron and CK the PDF of this talk, so anyone can have it and use it as you want.
That would be awesome.
And I'll make sure those 2 books are on a slide, which I forgot to do.
But
yes, thank you.
Great. Well, thank you very much, everyone.
Great audience.
Thank you, Neil.